right? So we're looking at the universe at whatever scale it's uniform. For example, in this room, certainly things aren't uniform at our usual ordinary scale. I'm standing over here, here's empty space, here's a table, here's an empty space. It's not uniform distribution of matter energy. But if I move a little bit away from the room and kind of look at it, on the average, maybe I can see, kind of a bunch of stuff. And I can consider it almost kind of spread out equally. The same thing if I'm moving out of the solar system. In the solar system itself, I mean, you see a thing there, a clump there, stars, planet, mostly empty space. As I move away from it, the solar system as a whole might kind of take on, if I look in time-lapse photography, some kind of planar spread of mass almost. Same thing, move away from the galaxy might look like some kind of roughly uniform thing, but then you have a vast empty space between galaxies. Then I move away from those, and I see clusters of galaxies. And I look at them roughly as kind of one uniform distribution of matter. And then I look over there and see another cluster, and over there another cluster. And if I look far enough away, I'll see like clusters, kind of like neighboring dots. Well, think of all the galaxies or galactic clusters, all right? Whatever scale is the appropriate scale. Either each galaxy is a particle, or each collection of galaxies, or each collection of collections of galaxies is a particle, a one-point particle. And we're going to look at all these particles, and they compose some kind of like a gas of particles. So the model of the universe in the approximation that's used generally is just a bunch of points, a point matter representing a point of space, kind of, and they're all these point matter particles interacting with each other. They're not in the field of some big mass, they're all in the field created by all of them. What we want to consider is their interaction with the greater field around them, which in the case of the spherical symmetry vacuum that we were talking about was the mass that they're attracted to. In this case, it's the collective field set up by all of them that each one is reacting to. And what we're going to look at is what happens. And we want to look at two neighboring such points. Remember we spoke, if you look at this room, a person here, empty space here, and so on. If you look at, so it's certainly not homogeneous. But if you look from space at a city, it's roughly like an average density of something or other. But then you look at the rest of the Earth, it's not average density, but you look at the solar system, you have a planet, the sun, it's not at all uniform. But if you look far enough away, then you can consider it to be some kind of mushed out average density something. If you look at the universe and you take each clumping, whatever that clumping is, some cluster of galaxies, another cluster of galaxies, another cluster of galaxies, and we consider those dots, points, gas particles. If you look at the universe from a scale at which the whole thing is roughly average density, you can think of the universe as the collection of particles at some scale on which the universe is presumed to be basically homogeneous, isotropic, spherically symmetric, where each particle represents galaxies or clusters of galaxies or clusters of galaxies. We want to see how it behaves under its mutual effect. What effect? Well, the effect of its matter energy. The gravity thing was simple. The situation that we took was a source, and you had two particles which weren't really, you didn't consider the gravitational field that each one created, only how they interacted with the source, not how they interacted with each other due to their own mass. They were like test particles. But due to the field that this created, they accelerate towards each other, without even taking into account the fact that, of course, any two particles, due to gravity, would accelerate towards each other due to their own mutual attraction. But we're not considering their mutual attraction, just the fact that they accelerate towards each other just due to the attraction of this one and both of them. Okay? What we do, instead of looking at a mass creating curvature of space-time and then taking two test particles which don't affect each other directly, but both are affected by the field created by this, and therefore have a tidal acceleration, what we're going to look at instead is a collection of particles, all of them equal to each other, not in the field of some bigger mass, but in the field that all of them create together as a whole. In this case, what we're going to be talking about in cosmology, we're not going to be talking about a field of one thing acting on a bunch of other things which don't have their own fields. We're going to be talking about the collective field set up by all of them together. Some kind of like a holistic picture. The whole universe contributes towards creating some roughly uniform field. And then you have each particle, each gas particle, so to speak, each cluster of galaxies, whatever, within that field.